This video is part 2 of Chapter 6, Independent Groups Designs for PSY 222, Research Methods in the Psychological Sciences. Now we're picking up kind of in the middle of the conversation of how it is that experimental methods allow us to create a situation where we have higher and higher levels of internal validity, so that we're more capable of making causal interpretations of our findings. In random groups designs, we have to be careful to avoid taking a group that already has sort of a characteristic associated with it and then randomly assigning members of the whole group or portions of that whole group to a particular experimental group or a level of the independent variable. So for example, if you were doing a community study and you wanted to sample from different groups within your community, like church groups or political organizations, for example, you would want to make sure that equal portions of each of those groups landed in each of your experimental conditions. So if you take an entire group, though, say you sample one church group and put them all in one condition, then you go to another church group and you put them in the second condition, and another church group and you put them in the third condition, you have harmed your internal validity because there could be naturally occurring differences between those intact groups. Another example might be if I was studying a curriculum and the impact of that curriculum. I may have one version of the curriculum, a second version of the curriculum, and a control curriculum. If I take one section of my intro class from Monday, Wednesday, Friday, and I assign them to condition 1, and I take my Tuesday, Thursday class and I assign them to condition 2, and then I take Dr. Meyer's Tuesday, Thursday class and put them in condition 3, by assigning those intact groups to the 3 conditions of the experiment, I can't control for any naturally occurring differences between those groups. So instead, what you would need to do is to randomly assign individuals across those groups to all of your experimental conditions. Block randomization, which was where we left off in part 1, is a way of increasing your internal validity because you can balance some of those additional variables that may come with the naturally occurring groups that you may be pulling your samples from. So it enables you to do an extra layer of randomization, basically. Another area that can harm internal validity is subject loss. Basically, subjects that no longer are useful to you. It can come in a number of different forms. Your authors talk about the difference between mechanical loss, and I have a concrete example of this from one of my SEE groups last year. They were looking at heart rate variability, and subjective stress measures. Their independent variable was the use of a weighted blanket. And one afternoon, the heart rate variability data there was a mechanical failure in the device that recorded the data. And so they lost a whole chunk. So it was several subjects worth of data for that particular dependent variable. So that's a mechanical subject loss. In years past, we've had other issues where data was corrupted. In a lot of this was physiological recording data, or the computer had some sort of failure during data collection, in online data collection. All of those are examples of mechanical subject loss. Now, selective subject loss is a little different. It can occur in a number of different ways. As your authors describe it, you can lose subjects across conditions. Sometimes, due to timing or other kinds of factors. Second, some characteristics of subjects may make them more likely to drop out or to fail to respond. This can happen in some research studies where they are multi-part, so that there may be subjects who are, say, much busier in terms of their academic schedule. They are more likely to drop out of a multi-stage project than subjects who have more time. So it's a different factor associated with those subjects that makes it more likely for them to no longer participate. There can also be certain characteristics of subjects that are themselves related to the dependent variable, and that can be a source of subject loss as well. Selective subject loss is actually a threat to the internal validity of the experiment. Mechanical subject loss, while it can be really super annoying and devastating when it happens, breakdowns in the mechanics of collecting data are not an internal validity issue. They are a problem that needs to be solved, and while you may lose data points, you don't have an interpretation problem. When you have selective subject loss, however, you do have an interpretation problem, because regardless of whatever the selective loss cause is, what you're identifying when you identify those selective losses, you're identifying a confound. Basically, the characteristics of those subjects that made them more likely to not persist in the study or to be removed for other reasons means that any differences you later find through your statistical analyses are harder to interpret. Some other things that are threats to internal validity are what are called demand characteristics and experimenter effects. Demand characteristics, that's the label that we give to cues, hints, whatever that participants may pick up on in order to make inferences about what they're expecting in the study. Participants in experimental research, especially laboratory research, they may in their own minds think, what is actually being studied here? So they're attuned to the cues that may be present in the environment that suggest how they're expected to perform. And that can then affect how they actually perform. Now, obviously, we want to keep demand characteristics to a minimum. You want to ensure that your data collection situation is such that you are not telegraphing in any way your expectations about subject behavior. Experimenter effects are the ways in which the expectations of the experimenter themselves can encourage subjects to behave in a way that's consistent with their expectations. And in some cases, this can have a profound impact on your outcomes. If you are, again, telegraphing, it's kind of like a quarterback tipping their throws, where the defenders can, follow where the eyes are tracking and they know which receiver they're going to be throwing to. If you are an experimenter and you are even subtly communicating your hypotheses or your other expectations, subjects can either kind of go with that, or they can fight against it, depending on their point of view. So, like demand characteristics, you want to keep experimenter effects to a minimum, such that you will not bias the responding of your participants. This is one reason that in lots of research, it's a little more common in clinical research and in medical research, but it's also found in some other kinds of research design, but we want to have what are called placebo control groups. Obviously, the label there comes from medical research where you're testing the effectiveness of drugs, and your control group is given a placebo. In other kinds of research designs, we still use the word placebo, but we just mean that the participants are going to be receiving a quote-unquote treatment, but it's not of the kind that might influence it's not of the kind that we expect to have the same kind of outcome as the independent variable. So for example, in my stigma study, I have all three groups, they watch a TV show. I have two groups that are experimental conditions and one group that is a control condition. It's essentially a placebo control group. I have them watch a neutral television program that has no violence and no mental health content. Basically, they watched when weather changed history. So essentially, it's a placebo. And any kind of impacts that I might see, if I saw changes, I would have difficulty interpreting that. So placebo control groups are used to reduce demand characteristics, which involves subjects potentially kind of thinking through and thinking about what are the real intended purposes of this study. And then in order to control experimenter effects, you can use experimenters who are in fact blind to the hypotheses that are behind the study. And this is important in lots of different kinds of research where you want the participants, obviously you want them to not know what the hypotheses are, but then you also may want the observer to be blind. So for example, if you're having a researcher record information, you know, maybe they're doing an interview or they're observing people's behavior and they have a coding system they have to use to apply to that behavior. In order to prevent experimenter effects, you will want to train the observer rigorously on how to categorize the behavior, but you would want to avoid telling them what you are expecting to see in order to avoid having their own ability to objectively code the data biased. Now, what's the process of doing data analysis and interpretation when we've got experimental findings and we're comparing groups of participants? We use statistical analyses to do a couple of basic things. We want to be able to make a claim ultimately that manipulating the independent variable produces an effect. It changes the level of the dependent variable. We also want to be able to use statistical analyses to rule out alternative explanations. And mostly this comes in the form when you run a test, a statistical test, of being able to say with a great deal of confidence that the finding you've observed did not happen by random chance. Or the reverse, that the finding you're looking at isn't reliable, that it probably did happen by chance. Now, one thing that we do rely on, you know, even if let's say you run an experiment, you find the expected pattern of results and your statistical tests are significant, your job doesn't really end there. It's important to replicate findings, and that may mean you doing the replication, but even more importantly, having other researchers do replication, because that is the best way to show scientifically that the pattern that you detected is actually reliable. Repeating experiments and demonstrating that you find the same basic pattern of results is something that we refer to often as a robust finding. And it's really troubling when we find that research findings that have held true for a small number of tests, then later on replication proved not to be reliable. It's frustrating. And in fact, in social psychology, but in psychology as a whole, social psychology in particular, there's something called a replication crisis that's been the subject of a lot of conversation. And basically what's been found in a lot of areas of research is that many findings that were assumed to be pretty locked down, pretty robust, have not been replicated in other more recent rigorous tests. So replication is extraordinarily important because you could get a finding with a particular population at a particular point in time, and unless you do replication tests, you really won't be sure that your findings can hold up and stand the test of time. So what are the steps in conducting an analysis with a between groups design? And these are very basic. I will say that when you do your homework, when we're looking at t-tests and f-tests in Pallant, you'll see this in more technical detail. We're talking about it here in more broad design terms. So first, you do have to clean the data. Now, you got some experience with this in your recent Pallant homework. You have to check the data for errors. You have to look for outliers. So you're checking both for out-of-range responses, mistakes in data entry, but you're also looking for individuals whose responding may be so out of line that they don't represent the population. The second step, excuse me, it involves describing the pattern of data within your sample and across your groups. So we use descriptive statistics. If we're talking about quantitative variables, we use means and standard deviations. When we're comparing groups, we do hypothesis tests to compare means, for example, and then we also run effect size tests to show ourselves, how large is the effect, and in some ways, how reliable is it. We also present data in tables and graphs or figures as well, so that you can describe the pattern of data that exists. And by pattern of data, what I mean is, if I have 3 groups and I have a mean scale score on my DV for each of those 3 groups, I want to look and see what's the pattern, which group has the highest mean, which group has the lowest mean, what about the third group, where do they fit in? Do the means all look about the same, or does there appear to be a clear difference between one group and the others? Or do all 3 groups differ from each other? And then finally, use what's called an inferential statistical test in order to test your hypotheses. So after I describe my between groups descriptive statistics, and I can give a verbal description of the pattern of data, then I can use a statistical test to test whether or not my hypothesis that say dangerousness ratings in my stigma study, dangerousness ratings, my hypothesis says, should be highest in the group of participants that watch the stigmatizing program with both violence and mental health content. It should be lowest in the control group that watched When Weather Changed History. It should be probably in the middle for those who watch violent TV programming but no mental health content. So I used an analysis of variance to compare the means in dangerousness ratings across those groups. So that's what this third step is. Now, to dig down a little deeper, what we're talking about with these descriptive statistics, the 2 most common types of descriptive statistics that we use when we're comparing groups on quantitative measures. So remember what quantitative variables are. They're numerical. We're measuring something at least on an interval or a ratio scale. So we're going to summarize and describe that data in terms of means as our central tendency measure and a standard deviation as our measure of variability. Now you're probably familiar, I would hope you're familiar with what a mean is. It's an arithmetic average. You add up all the individual scores and you divide by the number of scores and you get an average. It's a standard measure of central tendency. You're going to calculate that mean score for each condition of the experiment. So if you follow my example of dangerousness scale scores for participants in my stigma study, each participant has a score on the scale, and then I'm going to calculate a group average for each condition of the experiment. Sorry, my dogs are being very noisy. How we report this when we're rating, means are reported as a capital letter M, and it is italicized. Now this is a change over the last decade. APA style used to have a capital letter X with a bar over the top of it, which is super annoying to type. So they've switched to a capital letter M that is italicized to represent a sample mean. Group means are sometimes presented with different values, but generally speaking, we report the means with a capital letter M. We use these summary statistics because we're not interested in individual scores. You want the group average in your various groups within your experimental design. So like in my stigma study, I want to compare the subjects that watched the bad episode with those who watched the violent episodes with those who watched the control episode of television. I want to compare the group, not the individuals. Standard deviations are a pretty commonly used measure of variability, and what measures of variability do essentially is you not only want to know what the average score is, but you want to know how spread out those scores are around that mean. So you can have an average, say on a group of test scores in a class, and if most of the people in the class scored right around 80%, and they're tightly clustered, that means you have very low variability. If, however, you have a wide spread of scores, some people scoring really high, and some people scoring really low, with a pile in the middle, then you've got more variability in the scores. Standard deviation is a measure that calculates the average distance of the score from the mean. Now, when we use means and standard deviations, we are making an assumption that you have basically normally distributed data, where your mean and your mode and your median all tell you the same story. If you have skewed data, you're going to be using different measures of central tendency, such as a mode or a median, and different measures of dispersion, perhaps a range or something like that. But generally, if we're talking about interval and ratio data, we can safely make the assumption of normality. Then we use means and standard deviations as descriptors. Standard deviation is now reported as a capital letter S, capital letter D, and it is italicized when we write. It's an acknowledgement that not everyone is going to respond the same way, but what we're trying to get a sense of is just how spread out are the scores. The higher the number, the higher the value of the standard deviation, the more spread out the scores are, and therefore the less representative the mean actually is of the whole group. If your spread is relatively small, if the value of your standard deviation is relatively small, that means that the mean is more strongly representative of the sample. Now, to give you an example, this is a pretty typical looking table that you might find in a research report. The title, Mean Aggressive Cognition, Standard Deviations, Confidence Intervals for 3 Conditions of a Video Game Experiment. So you have the conditions of the IV, of the independent variable, where you got rewards, punishments, nonviolent games. So here aggression is rewarded, aggression is punished. And then the third condition is the control group, where you're showing a nonviolent game or playing a nonviolent game. The means are reported on the measure, so mean aggressive cognitions. So on average, how many aggressive cognitions? And you're given the table. If you're the reader of the article, you look at the table and you can make an eyeball statement. You have more aggressive cognitions in the group that played the video game where aggression was rewarded than in the other two groups. But yet then you have to ask yourself the question, and the deviations are pretty low, so the mean is pretty representative of the sample. Then you have to ask, okay, eyeball, it looks different, but is it different enough? And that's where significance tests come into play. So here you've got the confidence intervals, the standard deviations, the means. The next step is hypothesis testing. Now before we talk about the inferential statistics, effect size is a concept as well as a statistical procedure that's important for you to understand. Having researchers, I mean, when I was trained, so I was trained in the late 80s, early 90s, we did not learn effect size as a standard thing to be reported in our research manuscripts. By the time Dr. Muller and Dr. Turco were trained, so we're talking later in the 1990s and into the early 2000s, effect size became more normative as a statistic that you needed to report. So what effect size does is it's a statistical procedure that allows you to estimate how strong the connection between the independent and dependent variables are. And it controls for sample size, which is an important thing for you to consider. Because if you have a very large sample, you can have a significant test result which suggests to you that you have a meaningful difference between groups, for example. But when you test the effect size is very low. Because effect size measures control for the size of the sample. Big samples basically make it easier for you to detect significant differences between groups. So one of the more common measures of effect size is referred to it with the lowercase d, Cohen's d, Cohen's d, sorry, brain lapse. It allows you to look at the difference between two groups and average the variability as you're doing so. Cohen's d, there's some typical guidelines for what we expect to see. So you can have a significant test result, then your next job is to look at the effect size values. If the effect is small, regardless of the significance level of the test, then you say if the d is equal to about 0.2, that's a small effect, and replication would be absolutely required to know the reliability of that finding. A moderate effect is a d of around 0.5. A large effect is a d of around 0.8. Just to give you a visual, I'm a very visual learner, and I didn't really find myself able to wrap my head around effect sizes until I looked at a picture somewhat like this one. Let's say you were comparing males and females on a spatial skills test. Think of games like Tetris that requires spatial skills, like rotating objects in space. It's long been contended that males have an edge on spatial skills tests. So let's say you find a statistically significant between groups differences between males and females on spatial skills. The effect size is going to have a great deal of impact on how you interpret that significant result. If, say, these dotted lines are the mean for the two groups, if this difference between these two groups, let's say blue represents males and red represents females, and you have a significant mean difference between these two dotted lines representing the means, but the effect size is only 0.2, and the overlap between the two groups is about 83%, that suggests that you should not put too much stock in the meaning of that difference between those two groups. If, however, as you move down here and look at these different images, let's say you found a sex difference this time between these two means, and you're looking at the blue being the males and the red being the females on a spatial skills test. What if the effect size was about 0.5? That suggests a more moderate effect of sex on this particular test. But still, the overlap is about 67%. So it's a moderate effect, but most people, regardless of their sex, score in roughly the same range. Now, if we go down here, if on my test I am finding this level of difference, now my overlap has dropped down to 53%. This is a pretty large effect that would be considered to be fairly reliable and meaningful descriptively. So if I had a test that detected that, I would be much more confident in saying that there was a sex difference than if I had a test which revealed an effect size of only 0.2. Now, what if you have an effect size that's ginormous, like 2, which is, hard to come by? Then, your level of overlap is really small. You are looking at a test that can really discriminate between two groups. And by discriminate, I mean tell the difference between two groups. Like knowing group classification could help you to pretty reliably say how people would perform on a given test. So following that theme, if I knew that I had males and females and there had been this previous statistical finding that males have an edge on spatial skills tests over females, but the effect size was 0.2, I wouldn't have evidence that suggested that based on my knowledge of this finding, I should I should preference males for entering into, say, engineering programs. Because the effect size is so low and the overlap between the two samples is so high, I have no justification for saying just because there was a mean difference that in one study showed a statistical result that their performance would actually be meaningfully different. In a lot of sex difference studies, this is what has happened, is that you can find a statistically significant difference between the groups, but the effect size is so low that the result is meaningless. Even when you have moderate effect sizes in some of these sex difference studies, still you're looking at a very substantial number of people who perform pretty much identically regardless of their sex classification, and that means that you need to be very careful in applying that result as, say, a selection criteria. When you get down into this zone where you have much higher effect sizes, which in sex difference research is almost unheard of. Most of the findings in research on academic skills, for example, are in the low to moderate effect size range. Rarely, if ever, are you going to find these kinds of effect sizes in sex difference research. But if you got into this range, then you are more safe in being able to make judgments about cause and effect or about the meaningful differences between groups. And we're going to wrap up this section with a brief word about meta-analysis studies. And I've often said to my undergraduate students, meta-analysis is kind of above your pay grade. Meta-analytic research is something that it's a higher level of analysis. It involves summarizing and comparing effect sizes that are coming from multiple experiments looking at the same issues. So if you have, say, 50 studies that are all looking at the same independent and dependent variable combinations, and they've all reported findings and they have reported effect sizes, you can use a meta-analysis technique to look at, as a whole, what do all of these pieces of research say when they're combined. You have to have selection criteria for which experiments to include. in terms of, how strong is their internal validity. You want to choose experiments that have high internal validity. You may have other exclusion criteria that have to do with exactly how were manipulations done, how were dependent variables measured, and so on. And what this allows researchers to do is to get a big picture view of, if we take all of this research and kind of put it on a level playing field, what do the combined results tell us about the connection between our IVs and DVs in a particular research area? So that concludes part 2 of chapter 6. I'll see you again for part 3.